having Keijo Heljanko, professor of University of Helsinki. He's also vice director of the High Data Center, whatever that is called. I know it seems to have forgotten, but I'm sure that Keijo will tell us more. So he has been doing really noteworthy work on parallel distributed computation in data science, and looking forward to hearing more.
Thank you, Sami. So this is basically some slides that I'm reusing from my talk in a SINGPRO seminar, which is one of the latest seminars on this project. So this is a joint project with Aalto University Chemistry Department, where we have adjunct professor Iiro Harjunkoski and his postdocs Teemu Ikonen and Jose Mostafe, and then myself from University of Helsinki and my postdoc Tevodoros Deneke. And this is one of these Academia of Finland ICT program projects that's running for 2 years and is now coming to a close. And the project name is SINGPRO. And the idea of the project is that it's synergistic and intelligent process optimization. So Iiro Harjunkoski and his crew are more towards the, let's say, operations research. And they're in the chemistry department looking at things like, okay, how to optimize different industrial processes, for example, different chemistry processes, different processes in actually paper machines and whatnot. So, so the idea of the SINGPRO project is that what we want to do is do basically planning and scheduling for various industrial processes using traditional methods combined with machine learning and analytics from the big data. So the basic idea is that the analytics is actually collecting data from the real life processes and getting better statistics for planning and scheduling. And the basic idea in here is to try to optimize things like energy consumption, get throughput better, get better maintenance, etc., etc. So that's the high-level goal of the project. So the targets are to show that big data technologies can be deployed together with optimization strategies to close decision loops in automation. And these are kind of initial results on this 2-year project. The results can help define future research needs. We've collaborated with Finnish industry on piloting the methodology. We've worked both with equipment providers of the industry and also with real process people running things like paper machines. One of the challenges there is how to get access to real data, how to get access to industrial data. And this is then to create collaborative concepts that are reusable. So here's the team again. So adjunct professor Iiro Harjunkoski from Aalto Chemistry Department. He also has a position at ABB Corporate Research in Germany. So Iiro has 2 hats, both an industrial hat and an academic hat. Then it's myself and the 3 postdocs in question. So, so the highlights. What we want to do is we want to do online reactive and anticipative tools for sustainable and efficient operations. So how to optimize different industrial processes. And this requires you to basically create interfaces between big data analytics and machine learning, resulting in more agile, self-aware, and flexible decisions. And what you want to do is you want to combine first principle models. In here it means more like mathematical optimization models, operations research style models with machine learning. And we want to create, in data-driven fashion, models of normal process behavior and predictive models of process disruptions. So let's see how far we got in the project timeline. So that's the basic idea, that what you want to do is you want to use data analytics to gather historical data of let's say, a production plant, and use this data analytics to create various statistics about the plant that you feed into the mathematical, let's say, operations research style optimization planning problem. Once you have a plan, then what you get is you get different plans, and then you figure out how to evaluate them and what kinds of predictions would you have for things like failures that could happen in the different machines that are being used. Then you run the process with a particular plan, which gives you online data, and then the idea is to feed back that new data into the planning model, and how to do this, and for example, when to start replanning your production is one of the questions that we try to address in the project. So process is running, you gather data, you collect better analytics data, and then you optimize. So, okay, so there's various questions we want to answer. First of all, could we do better planning by knowing more about the process, for example, utilizing the real-time data? And this is something where we made fairly good progress during the project. So here's one of the problems that actually came up in the paper machine case, that we had actually real access to real data of a real paper machine for 1 year. So we got more like 1,000 sensors worth of data sampled every 10 seconds. And one of the problems in those paper machines is that what they want to do is they want to create different grades of paper, so different thicknesses with different coatings, and you have some deadlines on when you do want to deliver each one of the paper kind of batches the machine produces. And one of the challenges is that it takes different amounts of time to move from one paper grade to another. So for example, if you're producing this grade 7 and you want to go to grade 13, it seems to take a lot of time. However, if you want to move from grade 7 to grade 14, actually it's fairly quick. And we could compute this kind of a matrix, like these are the changes, how you change from one paper grade to another from historical data. So you do historical data analysis for a year, and you get statistics that, okay, if you move from one product to another one, how long a gap do you have between, right? And then you notice that many of these are actually never used. So the question is, okay, are these never used because they never appeared last year, or are these transitions between grades never used because they're particularly difficult? Okay, so what we do is we use this historical data, and then we try to use this in a planning model in a way that favors the grade changes that happened last year. And also, instead of using like a very crude model that does these paper grade changes using kind of guesstimate numbers that are over approximated, you actually use the real numbers that have been observed in production. And now you do the planning that, okay, each one of the products should be on time, etc., etc. And you want to do this planning with the, let's say, the better accurate statistics instead of statistics that are just guesstimates on how long a grade change takes place. And that seems to work fairly nicely. So instead of having this kind of, okay, you move from any grade to any grade. You actually prefer the quick changes from one grade to another that we know are quick by historical data. And by doing this, we can do this data-driven model where instead of running all possible grade changes, we actually can only take the grade changes that have been historically made. And for this case study, that actually was sufficient. We didn't have to invent any new grade changes. And we get kind of provably optimal model with these statistics compared to, let's say, actually running the optimization for the full model, in which case you get the worst schedule, and that schedule isn't provably optimal. Okay, so that was a success story in a way, that by using the statistics you can actually schedule the paper machine better. But it doesn't have much machine learning. It's just kind of, it collects statistics and then does operations research style things in there. Now, the other approach that we took a stab at is rescheduling. So the question is, in a process you might have new incoming orders. Like, you know, you've got to produce some products with certain deadlines, but then suddenly you get a new order with a new deadline. And the question is, okay, do you want to reschedule your process? And one of the challenges there is okay, if you have limited resources available for the scheduling, when do you want to trigger rescheduling? And at what point do you want to run, let's say, a heuristic algorithm that's quick but doesn't actually potentially give optimal schedule? And when do you want to run, let's say, a more costly mathematical programming algorithm that is better to create, let's say, a more optimal schedule but takes more computational resources? So here, what we did is really a tiny little case study where we used reinforcement learning for online rescheduling decisions. So the basic idea is you have this reinforcement learning where we have an agent that can take actions on an environment, and what you get back is a state of the environment and some rewards on your actions. And in this rescheduling thing, the actions are actually actions about how to optimize the planning. So when do we try to reschedule things, and when do we, and with heuristic or with more complex methods. And so the machine learning in here is actually trying to learn, okay, how frequently should you re-optimize, and in what kind of scenarios. So that's the basic idea. So what do you want to do is kind of, you want to have some kind of a model which reads the changes in the environment model and takes as output rescheduling decisions. So the things that we say can be inputs are things like deviations in optimization parameters, so processing times or material yields. If they change, then maybe that might trigger a reschedule. There are discrete changes in the process environment, like new orders are coming in, equipment might break down, that might have to trigger a rescheduling of the process. There could be state of the optimizer. We might be running out of computing resources, in which case it might make sense to not run the most expensive algorithms, but use heuristic planning, etc., etc. And the actions that this machine learning model wants to take are things like, okay, even though there was this change, we don't want to reschedule, or do we want to run a heuristic algorithm to let's say, tweak the existing schedule a bit, or do we want to do mathematical programming? The other things that a machine learning model could figure out are things like, okay, what's the planning horizon length, and how much CPU time do we give to the optimization algorithm? So, so rescheduling, timing, and optimization strategy are the things we try to learn. So far, this is more of a conceptual thing rather than something that is yet full-fledged. But we have some results. There's now a paper submission where we're using this neuroevolution of augmented topologies, and basically the decision space is just, okay, when do you trigger rescheduling, and how much compute time do you allocate for this? And the optimization algorithm we run here is actually this kind of an ant colony optimization, where if you allocated more computing time, it actually gets better schedules. And in some of these case studies, instead of like scheduling periodically, in this case study, it makes sense to schedule more, let's say, in the beginning of the schedules, and the neural network does scheduling less frequently, but using more computational time and early on. And through that, you get better schedules for this tiny case study of ours. Okay, so that was already kind of putting some machine learning into operations research context. Okay, so then we have this thing like, okay, is it better to dynamically generate accurate statistics on process behavior every time we want to schedule? And here I'll be very brief. We had a small case study on this openly available data set where the idea was to estimate taxi trip durations, and then we did a kind of model of the expected taxi trip durations. And of course, the more accurate you can make those statistics, the better you can do your prediction model. So for the interest of time, I'll skip the details there, but that's something we worked on open data. Then comes the, let's say, most ambitious and the one where we have more questions than answers. Okay, so one of the questions the paper engineers posed to us is that, okay, can you predict unplanned breaks in production based on the data they have? So how many incidents can you actually predict and avoid? And this is something where currently we have to say that we didn't manage to solve this problem during the time frame of the project, but we made some progress. So okay, so what's the idea? So you have some raw data. In our case, it's actually real data from a real paper machine for 1 year. So what do? We clean it up, we scale it, we do some feature extraction, and then we have data on some selected variables. Then we do training, and then of course we have the standard machine learning kind of approach where we then evaluate the model on unseen data. And then the predictions in here are that, okay, are various variations of is this machine going to have an unscheduled break, so a production failure in the near future. And that's a really tough problem. Okay, so what's the pre-processing? So ideally, we want the data to be arranged as follows, that you have different timestamps. In our case, it's timestamps every 10 seconds. Then you have various number of sensors. In our case, it's more than 1,000 sensors this way. Yeah, the data basically is 10 seconds sampled for the year. Unfortunately, the data is not in that format. So actually what we get is actually kind of compressed data where what we get is we get a particular sensor number, we get its value, and then we get a timestamp. And these sensors are actually not all sampled at exactly 10-second intervals. They are sampled at, some of them are sampled every, every half a minute, for example. Some of the tags are also delta compressed in a way that, okay, if the value would have been the same, then the data is not in the log file. But overall, we get more than 3.5 million tags a day. So 1.4 billion tags over a year, more than 1,000 sensors. So what you do is you translate from this delta decompressed version into this normal presentation, and that grows the data volumes quite a bit. Then you have to decode various things. What's the status of the machine? What are the different sampling rates, etc., etc. What to do with missing values, and whatnot. So then we do pre-processing, we do cleaning. We, for example, something that we needed the experts' help with is for example, if we have a paper machine, it seems that this is a typical case, that you have normal production and then you have a break. So this is like, okay, unplanned break in the production. But what we see often is that if you have a break, then suddenly there's a sequence of breaks, because what's happening is that there's probably some problem with the machine and the operators are trying to fix it, and then they try to start running and they manage to run for a couple of minutes and then it breaks again and whatnot. So actually, if we try to predict this break, then if we know that there's some signals that correlate to a break in the near future, then we're pretty certain that there will be a break, actually. So actually what you have to do is you get two good results if you try to predict these breaks. So the interesting breaks are those that are the first breaks in a sequence. So you want to actually clean up the data volumes in such a way that you require lots of clean production until you hit a break. Right. Then you have to worry about different things like there's signals at different amplitudes and whatnot. Okay, so prediction. Can we distinguish a break from non-break? So this is actually trivial. So let's say you have this kind of a break situation and you want to see if you're in here or in there. Then this is trivial. You can easily teach a machine learning model this. Why? Because in the break case, you will probably find some pumps that are not on, for example. So if there's a break, then probably you will not feed the machine some pump fiber and whatnot. So yeah. So this is trivial in machine learning. But it's highly influenced by signals, highly correlated with the break signal, like pumps and whatnot. And it doesn't provide any additional information. So even though you say, okay, I can predict the break without looking at the break signal, well, that doesn't really help any. What's actually more useful, but much more difficult, is trying to predict, looking at data only, whether we're in the middle of a production run from whether we're fairly close to a break. And this is something we tried to do, but it is really difficult to get this right, and we're getting fairly low prediction accuracy. So the thing we tried then is instead of using this model as such, is to look at the model and look at the features used by the model, and trying to figure out that, okay, could those be fed back to the process engineers to see, okay, the machine learning model is using these sensors to figure out whether we're in here or in here. So it might be that your breaks are due to these kinds of things in your system. So the root causes are the things that we're after. We're not able, yet at least, we're not able to do a fully, let's say, accurate modeling and prediction of these two cases, but we're able to get these root causes. The problem with that is that these root causes need domain expert analysis. So even though they look promising to us, it's not clear without the paper machine process engineer to see, okay, are these interesting enough? Thankfully, we had very nice support from the paper machine side, so we could schedule meetings with those people every couple of weeks, and we have some input for them, but not. This is by far not done. Okay. The other thing that we took a look at is to look at look at signals that have time varying correlations. So signals that where the correlation changes with different delays to the break signal, and using those in prediction of the breaks. The idea is that these signals might be due to different kinds of, let's say, slow changing things like, let's say, pipes getting blocked slowly in the process and whatnot. And if we do such things, we can figure out that some of the features do reflect degradations in performance of the plant, and that improves prediction accuracy somewhat. But it doesn't solve the problem. It's still, the prediction accuracy is still fairly low. So findings, data cleaning is difficult without domain expert help. So if we wouldn't have the machine learning, the process engineers in the loop, we would have declared success many times, because our machine learning model would have cheated and found some things that are not true. Just an example, one of the things is that there needs to be a gap between these two, because this break signal actually is not sampled frequently enough, so that actually some of the pump signals actually change their values some seconds before the break signal. So if you use a machine learning model that looks at the pump signals, then those are able to predict the break a bit sooner than the break signal, because, well, the break signal is not sampled frequently enough to figure that out. So so we could have created a machine learning model that would be very accurate in predicting breaks. However, when we showed that, okay, these are the root causes it's using, then they were saying, oh, but these are the pumps. Okay, so actually, data cleaning is difficult without domain expert help. Prediction accuracy is still very low. It's a very complex process, lots of sensors. We have a couple of different approaches on looking at root causes. Predicting a root cause requires a lot of domain expertise. There's a lot of data cleanup that needs to be done. So break signal sampled at roll frequency, which was detected only at looking at the correlated root causes. Okay, so just a couple of slides on the root cause analysis. So what we use for root causes are, first of all, the machine learning model root causes reported by the machine learning library. The features used by the machine learning model. And then the other thing that we're looking at is different variants of using Granger causality. And what's that? So the basic idea is that in Granger causality, what you try to do is you try to predict a time series X, or let's say time series Y. Which way do I have? Okay, let's move to this slide. You're trying to predict a time series, and you're trying to predict a time series Y, and what you try to use is to use a signal X to predict the time series Y. And if you're able to predict the time series Y better by using the time series X, then you say, okay, X Granger causes Y. And this is the case in the linear setting, but we've been playing around with different variants of this in the machine learning setting, where we do various tricks to try to figure out that, okay, if we remove some of the signals from the features, which ones of those make the predictions worsen the quickest. So if you have a machine learning model and you replace one of the signals with actually, in our case, what we use is just a simple permutation of that signal. If that causes the prediction accuracy to go down quite a bit, then probably that signal is more valuable for the machine learning model than the other signals. And we've been using this to a certain degree, and it seems to work nicer than the features given by the machine learning libraries themselves. But we still have to publish a paper on that. That's in the works right now. Okay, so let's move forward. Okay, so then there's this question, are there decisions that can be excluded from the optimization scope? And I'm running out of time, so I'll skip this. This is mostly work by our colleagues. But there are things like, okay, you want to do selective maintenance, and then you have this notion of infant mortality, that you have some components that fail very quickly when they're young, and then their, let's say, failures stop happening, and after they become old, they start failing again. And then the idea is that if you have like a process like this, then when do you want to replace different components? So let's say this is like a linear sequence of things that need to work for this process to work, and then there's some redundancy in these stages. And the question is, okay, if you want to do like yearly maintenance, which ones of the motors or pumps or whatnot do you want to replace? And if components have high infant mortality rate, then you don't want to replace motors that have been there a while, because then they are past their infant mortality. And then what you do is you can write your optimization model on what components to replace, taking that into account, and get kind of extra constraints on the optimization model, taking infant mortality into account. Okay, conclusions. So we see clear benefits from using more advanced methods to process historical online data. For example, this grade change optimization seems to be really something that can be useful. And we've been using AI machine learning methods to improve accuracy of scheduling, improve predictability of processes to help reducing the domain of some large-scale problems by figuring out that, okay, for example, these are the most commonly used grade changes, for example. The data-related work is still very problem-specific. The value of the data is difficult to estimate, and we need collaboration across disciplines. So on the break prediction, the paper-machine breaks are really difficult to predict, and we need domain expert help in many cases of the problem, specifying the right questions to predict, specifying data cleaning principles, and especially once the machine learning model gives some results, evaluating the potential root causes, debugging machine learning, data cleaning, identifying potential root causes. So in that context, machine learning cannot be successfully done without access to domain experts. Otherwise, we would have declared victory without solving the real world problems. So you need the process engineers there in the loop to keep you honest. That's what I have. Thank you very much. And this is Academy of Finland sponsored project. So thank you. Questions?
Maybe I could ask the first one.
Yeah.
So in the first example that
Yeah.
you showed, where you are, I mean, how I would see it is that you are building a model of the world, which is the machine.
Yeah.
And doing that based on kind of afterwards, after the data has been collected, and,
Yeah.
and then you do scheduling on top of
Yeah,
it.
yeah.
So the zeros in here, I mean, to me they are unknowns, right?
Yes, they are unknowns.
Yes. So did you think of, I mean, in principle you would now consider that you have a exploration-exploitation trade-off here.
Yeah.
And you could start doing the experiments, and then the question would be that how would you as quickly as possible find the routes that you haven't found based on the historical data yet?
Yeah.
Would this be interesting to the people you are working with?
Potentially. The thing is that making these experiments is really expensive because that's a real paper machine with real production. So, and the question is when we ask the so of course the current scheduling model has some numbers. So there's an existing scheduling model that has a number in every zero, right? But those are like guesstimates given by the persons who are involved in the process design. So in here the things that we use, and actually for this problem it happens to be satisfiable, is that we use historically known good schedules. And yeah, it would be interesting to see how to fill those zeros with real statistically valid data rather than the guesstimates that are there in the, let's say, the current production scheduling system.
I would definitely not throw out the guesstimates, but I would kind of acknowledge that they are uncertain.
Yes.
And somehow quantify the uncertainty before doing the exploration-exploitation.
Yeah.
But so, yes, I fully appreciate that this is a running paper machine, but the question is that they have decided to run these experiments that there are in the table with some constraints in mind. So of course, if you would put those constraints that they use into these exploration,
Well,
you would sell it to them that it's going to work better.
Yeah. This is like those numbers are the numbers they used in previous year's production, basically. So those are the statistics from last year.
Right. If you would now know what are the constraints by this, they chose exactly those experiments.
Yeah.
And put them in, and then run the data.
Yeah.
I would be, by the way, very interested in that.
Okay.
Any other questions?
Yeah.
You have mentioned that you used several machine learning models for break predictions.
Yeah.
What kind of machine learning models?
So these were there's random forest based ones and then LSTM based ones that we used so far. Nothing really fancy. Yeah.
Okay, so you said that it was hard to predict break.
Yeah.
I guess people have been trying to think about this for 100 years. I don't know.
Yeah.
How
Yeah, these are expensive machines, yes.
So it's like some very, very like motivated and smart people have already been trying to figure out
Yeah,
how to
yeah.
do breaks.
Yeah.
So maybe it's a measurement problem. Could you utilize machine learning in acquiring some new data that hasn't been available? For example, some real-time data that's so fast that humans can pick it up. Is there a venue to like approach the problem in that sense?
Yeah, that okay. So what these guys would really want in the end is a fully automated system that.
Sure, and use the old data that has
Yeah.
been like tried for 100 years.
Yeah.
It's not going to improve. You said that it didn't improve, and probably like human brains have been thinking about that for a long time.
Yeah.
What are the chances?
Yeah. So one thing that people might be looking at is things like anomaly detection. So trying to figure out that, okay, now the process is in normal operation and now it's in anomaly situation, and then maybe having a red flag being raised if you have some anomaly, and then saying to the operators that, okay, now you're outside your normal mode of operation. But it's quite interesting. Okay, so this is not kind of a story that I heard, is that one of the interesting things about paper machines is that the operators, each one of the operators is configuring the paper machine slightly differently, for example. So one thing we haven't taken a look at is for example, what are the settings that they are using that might cause breaks to happen more frequently? Because actually there isn't a standard config that everybody runs. It's like, how were they saying? It's like concert musicians. Everybody plays with their own style. So you have various knobs you can tune in the multi-million-dollar or multi-tens or hundreds of millions of dollars machine, and then run it to your own good. And that's the question is, okay, could we use machine learning to figure those knobs out, which are the best ones? But maybe that doesn't answer your question.
No,
but
maybe my question was to apply some, like one word, new data.
yeah. Yeah, we'd be happy having more sensors and more frequent sampling rates, but it's not clear that will help. It's not obvious. Some of the things we haven't done that are there is, for example, there's some delay in the process, and we don't have a very intricate delay model. So one of the things we could do based on the data is to do a more accurate delay model, because there's tanks and whatnot. So you know that if you put stuff into the tank, it's going to come out of the other side later on, and yeah. Things like this, that it might be that you're able to reverse engineer the process using machine learning models, and then let's say do a better mathematical model of the process behavior, and then use that to predict some things. Yeah.
I'm sure the new data would help, but I wouldn't lose hope completely that everything that is in the current data has been taken into account.
No.
Probably are using a limited model.
Yeah.
Combination of that and machine learning.
Yeah.
The residuals or something.
Yeah. So.
That one as you avoided it.
Yeah. So yeah. It's like that. Let's say there's so much data that the current process analysts are not able to exploit it all with their standard tools that are more like correlations and not very. So machine learning hasn't really been thoroughly used in this context.
Also the so-called human-in-the-loop machine learning, reverse engineering, what are the operators actually doing?
Yes.
And taking that into account as prior knowledge.
Yeah.
That's also something that I believe that people at the additional people in the
Yeah.
haven't been working on.
Yeah. So we have access to the data, so if there's people who are interested, maybe something could be figured out.
Let's have a chat about that. Also, you probably are interested.
Yeah, okay.
One more quick question, then we need to end. If there are none, thanks a lot, Keijo.
Thanks.